Good, welcome. So this third lecture, you see the schedule here, we'll discuss renormalization and then resummation in effective field theory. And indeed, the resummation of logarithms is something which Matt has already mentioned several times, and it's an important reason to use effective field theory. Yesterday, some of you asked, well, why go through the entire trouble? Isn't the full theory in some sense simpler? In some sense, yes, but there are examples, and we'll discuss an example from flavor physics where we really have to use this effective field theory to compute the physical quantity. Otherwise, you end up with these large logarithms. Before diving into this example, which will be a big quark decay process that we'll discuss, I want to discuss a little bit dimensional regularization. So I promised yesterday that we will compute the volume of the d-dimensional sphere because it's fun. And we will not really compute loop diagrams here. This is usually takes effort for those who have done it, but I will show you some results of computations and I will discuss some features. And to do this discussion, it's helpful to see a little bit what lies behind and why these results have the form they have. And for this, it's useful to discuss this dimensional regularization. I've written on the blackboard the names of the people who invented it. One reason for writing it is that otherwise I might not remember because two of them are not so well known. Pollini and Giambacci. These are Argentinian physicists. And then, of course, 't Hooft and Veltman, these are super known. And usually when people say dimensional regularization, they point to these. But Wolfgang Bietenholz, another Swiss physicist who is a professor in Mexico, actually looked into the history of this. And Pollini and Giambacci actually sent their articles first to the journal. They did, of course, less. The important thing that the Nobel Prize for 't Hooft and Veltman was that they were able to show that the standard model is renormalizable. Pollini and Giambacci, they did QED. They showed that this regularization preserves gauge invariance, but not quite as much as the other. Still, it's kind of an interesting history behind this. And I've linked an article about this history. This is called Revolutionary Physics in Reactionary Argentina. So Buenos Aires had a very good physics department and the universities there so were quite autonomous and good. And then there was a military coup. And the government said, well, of course, these scientists are all suspicious that the university is now under government control. And the rector refused, and the professors and students were sort of locking up at the university. Then the police came and beat everyone up, and about 1,500 professors resigned in Argentina, and basically the ones who could leave left. For example, Virasoro is a famous example, he left Argentina. And the guys were doing physics then, instead of at the university, at their home, which they ironically called the Institute of Name of the Dictator, but it was just their home, and so they were doing work there, and later at the other university. So that difficulties, difficult circumstances, but they did actually great work. They came up with this dimensional regularization that you should work instead of in d dimensions, in d equals 4 minus 2 epsilon. And as I said, they sent their article before 't Hooft and Veltman to physics letters, and you can imagine what the enthusiastic response of the referee was to this great development. Exactly, Will says it. The referee said, quit fooling around and go back to 4 dimensions. But they later wrote a second article, and so finally this was published. Anyhow, to frame the problem, if we do higher order computations in perturbation theory, in quantum field theory, these have the form of these loop diagrams. Say you have some external momentum P, and then you can have a loop momentum K, which flows around this loop. then I would have, careful with the zeros, then I would have the momentum P plus K flowing around the other side. And correspondingly, you get these types of integrals. Integral d dk, where the dimension is 4 to start with, but we'll change it later. And then here you have these propagators, k squared minus m squared. So this by cube theory that was mentioned by Matt, and here and already here you can easily see the problem with these divergences. So d is, forget about, you're not yet fooling around. D is 4, so this integral at large k goes like d4k, and that very large k is masses and momenta you can forget about. It goes like k squared. So it has 4 powers of the momentum in the numerator and 4 power in the denominator. So this is like an integral dk over k.
So that momentum at the top meant to be p minus k.
No, it's meant to be p plus k. So this momentum, I put here little arrows. So this momentum here flows like this and then flows around the other side. Maybe I shouldn't say it is, but let's check together. So I want to have, you've kind of seen some Feynman rules. One characteristic feature is that the momentum is conserved. So the incoming has to be the outgoing. So here there's a momentum P incoming. And since I'm routing this K this way, there's a K going here. So then there's a K here on the other side. But your answer would also be correct. So do a K goes to minus K, then this goes to K squared, and then you would have a P minus K squared minus M squared. So both of these are perfectly fine.
If you're in even
no. It's just K to minus K. Even if this is a one-dimensional integral, I could do K goes to minus K.
But does the measure change?
Yeah, but then you change it. So this goes from minus infinity to plus infinity, and then the boundaries would, and it changes back. No, the measure is fine. So this thing here, of course, at the lower end, there are these masses, so nothing happens at low, but at the upper end, as you integrate to infinity, there's a divergence. So there's an ultraviolet divergence. And one has to do something about it. Now, there are some techniques that one learns how to deal with these integrals in the QFD course, like Feynman parameters. So one can always combine denominators into a single denominator. So at the end of the day, if you do loop integrals, once you start combining propagators, the general integral that we need to define looks like this. Now, this is not the usual physical mass, but this can depend on momenta and other things after you combine the denominator. And then there's the power n here. And so if you know how to define these integrals, then you're good to go. And we have to define them in such a way that they're not just infinite, so that we can start computing, extracting the divergences. Once you have extracted the divergences, you would want then to take them away, absorb them into the couplings. This is the renormalization part. Good. And now you can ask yourself how to proceed here. And of course, the simplest thing is just to put an upper cutoff on this integral here. I should also say one other thing one does when combining things. So let me do this as well. There's a big rotation where one defines a Euclidean momenta I times k 0. Then with this I, this changes sign, and let's take the sign out. And this integral is really an integral in the usual r to the n or r to the d. Is the wiping device.
Okay.
So it's integrals like this, and this is now just an integral in r to the n. So these types of integrals we have to do. And so again, a cutoff could be, for example, something like this. I say this k squared has to be smaller than some lambda squared. And then, of course, this ultraviolet divergence is gone. But this cutoff has some severe problems. It's, of course, not unique at all how to put this, and it destroys all the symmetries that the theory has. It destroys Lorentz invariance. And even more importantly, it destroys gauge invariance. Basically, all the symmetries that Matt carefully constructed will be lost. All the unphysical, horrible stuff will be happening. And then there's a lot of work needed to restore. I mean, one can do it. You can renormalize, then carefully arrange things so that the unphysical stuff goes away. And in each order, you'll have to work very hard again. So it's not a good scheme to do computations. So this cutoff is only used in textbooks, basically. Maybe in different quantizations, things are different. But if you do serious computations, usually, especially with more than one loop,
cutoff is okay if you're only interested in the log.
Oh yeah, if you're only interested in the log. It's also, this cutoff is nice and physical in some way. So many textbooks will start with the cutoff because yes, it's ultraviolet. But we have to do something which is technically better, but a bit less obvious. It's intuitive. So this Polini and GPC, I can't even say the names because they're not famous enough. The first idea was, well, the first thing you could do is try to change this n. So how about, I mean, this integral is divergent for n c smaller or equal than 2. So I could put a little something here, and I could make the integral convergent. It's not bad to do this.
Now you're speaking d equals 4 when you
still d equals 4, so d is still equal to 4. I'm putting the d because then I don't have to rewrite the integral. But that will be the first idea. That was their first idea. This was used. This is nice because it actually conserves Lorentz invariant. So it's a better scheme, and for scalar theory would be okay. But it's not good with gauge invariance because there are things in the numerator and in the denominator. If you do it like this, you break this, and you get troubles. Now we'll tell you that we can also add terms in the numerator to restore this. So if I've seen it correctly, we published a paper called Denominator Regularization, where you go back to this scheme. You look at these integrals and you strategically include functions in the numerator of this parameter alpha, such that gauge invariance is restored. And if I didn't read the paper in detail, maybe you should give a presentation for me this afternoon or so. As far as I understand, you did the scheme at the one loop level. I don't know how easy or complicated it is to do 5 loop computations in the 10 rate. But this is one possibility, but it's maybe not the easiest one.
So just to say, it is on archive, but the referees have also been quite.
Presumably in your case is that stop fooling around and go back to D dimension. Okay, good. So that's not what we'll do, even though it's maybe the more obvious thing. These type of regulators are still used, for example, in the soft collinear effective theory. Often dim reg is not good enough, and you put additional ones here to be sure that everything is okay. And so then the dim reg idea is to evaluate instead, change the space-time dimension. So if you have a square here so that it's divergent, but we would be in a lower dimension, then it would also become convergent. So we now set E equals 4 minus 2 epsilon. That's what these people say. Actually, they said it 4 plus epsilon. That doesn't matter. Now, the only question is, can you make sense of this integral? What does it even mean to do this in 4 minus 2 epsilon dimensions? And the idea to do this is just to go to spherical coordinates. So we will take this IN. Fortunately, after doing all our manipulations, the integrand only depends on k squared. So it's very nicely suited. So I'll have an integral over angles in d dimensions, whatever these are. And then I have an integral over the length of this k. So I said k is the length of this vector here. And I integrate from 0 to infinity. This was ddk, so there's a k to the e minus 1. And then here I have 1 over a squared plus m squared. And now we're already in good shape. This integral, either you can work a little bit and see that it's related to a beta function, products of gamma functions, or you just type it into Mathematica. So these are some gamma functions. And the only thing that we still have to define is this integral over the d-dimensional solid angle, this omega d. All this integrated on omega. So let's now try to compute this. And to compute this, just stop me if you.
Should the side angle be d minus 1?
Yeah, good. It's a matter of convention. I call this the solid angle in d dimension, but of course it's the surface of the sphere. You're right. So it's a d minus 1 dimensional integral. So it's the surface of the 3-dimensional sphere, but of course it's a 2-dimensional sphere. So I'm sorry, but it's my convention.
In your defense, it's the same convention as Pascal.
So then it must be right. Now the trick to do this is to compute something completely different. And the thing that we will compute is the following Gaussian integral. The dimensions minus infinity to infinity. This x is now some dimensionless quantity. Now, of course, this e to the minus x squared, this is minus x1 squared plus minus x2 squared. So this factorizes, so you can write this integral as just the integral over the first component, dx1, e to the minus x1 squared. And there are d of these integrals. So that is the result. And I think this integral here is just square root of pi. The reason we did this is now we'll do the same thing as here, and we go again to spherical coordinates. So this integral also depends only on x squared. So we can also write this integral as again the integral over the three-dimensional angles in this x space times the integral over the length of this x vector, and then x to the d minus 1 e to the minus x squared. Still the same integral. And now we just have to compute this integral here. This is again something one could type into Mathematica. But one can also, let's change here and introduce a new variable y, which is x squared. Then this becomes integral 0 to infinity y. There's a factor 2 from the Jacobian, 1/2 here. There's also a factor x here. And so this is y to the d minus 1/2, but then another minus, so it's d minus 2/2 to the minus y. Now you correct me if I did it incorrectly. Now this integral, this is the definition of the gamma function. If this is some arbitrary argument a, this is just gamma of a. So this thing here is just omega d times the gamma function of d minus 2. Oh, the 1/2, I forgot. Yeah, there's the 1/2 here. So now we can solve and read off what this, what the omega d is. So the omega d is pi to the d/2, so the square root to the power d, divided by the other thing. So pretty cool. This is now the surface of this d dimension.
D minus 2.
D minus 2. So this is now this. Let me check whether it agrees with my notes.
Was it
yeah.
minus 1 in the power, and then it shifts by another one?
The definition, it is that there's a there's a -1 here.
Yeah.
So there it's actually d/2.
Yeah.
So with my intuition, I wrote the correct result, even though it's the wrong derivation. Because I've seen this formula before.
Yeah.
So now we can maybe do a table. Here is the dimension, and here is the surface thing. In dimension 1, this is equal to 2. Dimension 2, this is 2 pi. In dimension 3, this is 4 pi. Then in 4, it's 2 pi squared. Then it continues. You do a solve. Here is the dimension. This is the omega d. It increases first. So 2 pi is larger than 2 and 4 pi is larger than 2 pi. So it increases. But then ultimately it very rapidly decreases at large dimensions factorially. So, and this turning point, I think around equals 8 or so. So first, this surface area of the unit sphere increases, and then all of a sudden it turns around and rapidly goes to 0. I don't have a good intuitive explanation. I don't know. You start, as you go to 27 dimensions, there are more edges that you start cutting off from your sphere, and so it seems to, surface seems to become small. Anyhow, with this result and doing the other integral, we can now really write a result for this integral in that we need. Let me write this down and then we can discuss pictures. So the other sort of the radial part I didn't do in detail, but I can write down the result. Or maybe let me or the family, right? So you remember what the result is. So we know it's omega d, and then it only depends on this mass m squared. Now is a question of the day. This will depend on m squared to some power. What is this power? Okay, m here.
An instinctive reaction to this.
Yeah, exactly. Well, that's I rewrote it so that we can look at it.
Look at dimensions.
So there's an m squared to the power n in the denominator. So let me put a minus n here. This is from this. And then the k, of course, has the same dimension as the n. There are p powers of k here in the numerator. But since I write it as m squared, each k gives half a contribution, so plus 3 halves. So that is the
Just by dimension.
Yeah.
This is the only thing
it's
that
really dimension. Yeah, it's
I just
dimensional.
want to write out, there's d dimensions from the ddk.
Exactly. So if I just look at the energies, there is energy to the power d minus 2 times m. And just to make it confusing, I wrote it as m squared, so as energy squared. So I have to divide this by 2 and write energy squared.
And then we say that radial bit doesn't have any dimensions to its not.
The angles, no, they're dimensionless angles. So
It's not the surface area, it's the angular.
it is the angular surface, so it's like it's of the unit. Here. So it's like 2 pi is the integral over the angle, and it's dimensionless, but you can view it as the circumference of the unit. So. But you can really read off. So it's d powers of the energy here minus 2 n powers here. So you immediately get this dependence. And one of the great things is that this works. So even for the loop diagrams, it's very easy to see at what order what contributes. When I yesterday said, this power counting, even at the loop, everything is easy. Then Thomas said, well, but doesn't it depend on the regularization scheme? And yes, if I would put a cutoff here, then there are 2 scales, the cutoff lambda, the mass m, and the thing would be still have the same dimension, but it would be then some complicated function of lambda and m, so it wouldn't be clear what the dependence on the mass itself would be. But this is this, and the rest can only be a function of the dimension. And I will just write what it is. So that is this function. And now the last interesting thing is to now look at an example where there should be a divergence. So let's choose the I equals 2 case. I can keep. And then I have my m squared, and now I want to set this d equals 4 minus 2 epsilon, and this epsilon is the small regularizing quantity, and then I want to look at the limit epsilon to 0. So if I plug this in here, it's d half, so that's 2 minus epsilon minus 2. So that's minus epsilon. And then there's some gammas, like d half, 2 minus epsilon. And then there's a gamma of n minus d half, that's the same combination, except for the sign, so that's the gamma epsilon. And then the 2 times gamma 2. And so there's maybe 2 interesting things. One is that you get this dependence on m squared now to the power epsilon, and the other one is this gamma of epsilon here. And what one now does in this dimensional regularization, one first computes this. This computation as an integral, this is only possible if the epsilon is suitably chosen. So this epsilon has to be larger than 0 slightly, then I can do the integral. But if you look at the result, this is basically defined everywhere in the space of this epsilon. So you can view it as some function of epsilon. And now we expand around 0. And then what happens is you find that you get a 1 over epsilon. So there is a polar epsilon to this 0, which is a reflection of the fact that the integral is divergent. Then there's some Euler constant. And then there are more things. Is it the plus gamma Euler? I hope so. No, it's a minus. And this is just some non-constant 0.57. And I will show you results of such loop computations later. And you'll see these divergences, they have the form of 1 over epsilon. So, yeah.
So I just want to double check. So you substituted for D and set M to 2.
Yes, exactly. So this is the I2 at D equals 4 minus 2 epsilon. And now I could expand this in epsilon.
So I'm guessing what is the N? Maybe I've lost track of what N is.
N is just how many propagators I have here.
Okay, so
In this the diagram that I've wiped away a long time ago.
okay.
This has 2 propagators, so it's an n equals 2 diagram, which is actually a divergent diagram. So this would renormalize the mass, for example, renormalize the norm of the field. But if you had an integral like this with 4 propagators, then actually this would be ultraviolet finite. So it depends on which diagrams you compute, whether you encounter this divergence or not.
Okay.
But the nice thing now that we've introduced this, we can always find an epsilon so that the integral is well defined. We compute it, then we have the result for any epsilon. We expand around the limit we're interested in, there will be a divergence. And then of course we have to deal with these divergences, and what we do is we absorb them into the couplings and masses and parameters of the theory. Later on, in our case, into these Wilson coefficients.
Thanks.
Almost done with this. Few more things. It's a bit dimensional analysis is nice, of course, and it gives you this m squared to the minus epsilon. So, but this has a very weird mass dimension, m squared to the minus epsilon. And people prefer not to have this, but instead work with things which have the usual mass dimension. The usual mass dimension would be 4 powers here and 4 powers there, so it would be a dimensionless quantity. And so what people do is they typically, they're not computing this, but they introduce some scale news there. The renormalization scale, this is actually introduced together with the coupling, so this automatically will come. And then when we compute the integrals, you get combinations like this. And then instead of having this m squared to the minus epsilon, you multiply it by mu squared. So you have mu squared over m squared to the power epsilon, which is nice. And then neglecting the other factors, you get, let's say, 1 over epsilon here. And if you expand in epsilon, this thing here will be 1 over epsilon. If you expand this, you get a log. So you could write this as e to the minus epsilon times log. You expand the exponential, and so you get a log of mu squared. Yeah.
Will the term that's the gamma 2 minus epsilon, will that also eventually, if you expand it?
I'm just too weak to do it. Of course, we have to do it everywhere. I have to put the omega d in, put the d everywhere, and I have to expand. And it's very important to also keep higher order terms here, because I can have an order epsilon term from this, multiplying a 1 over epsilon from here, and then it's a finite contribution. So you have to expand everything up to finite order. The order epsilon you can usually neglect, because at the end of the day, you're interested in this limit epsilon to 0. So what we'll do, compute, have the divergence, remove it into the coupling, and take the limit epsilon to 0, and then finite pieces will remain. Like, and in some sense, the finite pieces are the most important thing. This is what will have the physics. But even from the divergent part, this generates this log. And these logs are interesting. These are logs which we will later resum. And a crucial element is that the divergence always comes together with the log. So if you know the divergence, you know the log, and vice versa. Yeah. So that was one remark. And the second one is, if you set this m squared to 0, then this integral doesn't have any scale. So if you look at integrals like this to some power like this without any scale inside, then what can these integrals be? They're either ill-defined, which might be a natural choice, but what happens if these are defined? So you could, for example, compute this in a region that is okay. Set the m to 0, then you have 0 to the power, let's say something positive, hopefully. And then you say, 0 to the power something positive is 0. So this function is 0. So all these integrals here are 0. And these are called scaleless integrals. So they're regularized to 0, which will be shocking. I think this is such a highly divergent integral, and it just gets regularized to 0. But this integral doesn't have interesting physics inside. If you would put a cutoff here, then of course, if I would put an upper cutoff, then there would be a scale, and then the integral with the cutoff would be lambda to the power d plus 2n. So it would be a pure cutoff term. So some divergence, I would have to renormalize this divergence away, and then I would be back where I was. So the nice thing is that such terms which do not contain interesting physics, they're just set automatically to 0. That is a very helpful property in computations, and people use this.
Sorry, can I ask a question on that?
Yeah.
So I really like some of the irreducible ones. So the scaleless integral, maybe scale is either 0 or infinity.
Yeah.
But so you have 0 there, and that makes very good sense when you do the dimensional analysis from the original integral for certain powers of n, right? So when the integral is proportional to m, say m to some positive power, and take m to 0, you get 0, and it's very natural. But if it's proportional to m to a negative power, you take m to 0.
Then I will change epsilon until it's m to some positive power. Then it's 0 again, and then I analytically continue back. So this is this is how we do it. I'm not afraid to go to negative dimensions, things like this. Sorry. Yeah. This is a bit, I mean, it's an interesting, yeah. This works consistently as far as we know and does not generate any.
I remember when I was first taught this, the justification given by the lecturer was that you should be able to use variable transformation and scale the integration.
Exactly, that is also a nice thing.
Replace k by k times.
Exactly, this is a nice exercise. But this scale transformation tells you that the integral is either 0 or ill-defined.
Well, yes. You start from the assumption that the integral is
If
defined.
it is regularized, yeah, if it is regularized, the only possibility is 0. So integral d dk, and then k squared to the power n. And now I do a variable transformation. K goes to lambda times k prime. And then each dk gives the power lambda. So I get lambda to the d. And then here I have to rewrite the case with k primes. So more lambdas. And then I have the integral over k prime. But of course, this is exactly the same integral as this. So then you get the relation that this integral I here is a different I. Jn is equal to lambda to the d plus 2n Jn. So and then you have this nice equation. Has to be valid for arbitrary lambda. And then the question is, what is the solution? 0 is the solution of this equation. So again, 0 is a consistent solution, but it could also be that the entire equation is just completely ill-defined.
It is also valid.
Yeah, infinity is the ill-defined. Yeah. Good. And the last remark is that I've discussed ultraviolet divergences here. But if I have negative powers of this n, I can also have infrared divergences. And also these infrared divergences can be regularized in d dimensions. So people use this for both. And this is again extremely helpful because if you do any computations in QED or QCD, the gauge bosons for sure are always massless. And so this generates divergences, which maybe at the end of the day go away, but the individual diagrams have also infrared divergences. And so this is very helpful that one can use it also for infrared.
This is one for n equals 1 and then I, and it seemed like it obviously makes it true for n equals 2.
Yes, again for n equals 1, something interesting happens. So n equals 1 is a divergent integral. It's even worse divergent. This was logarithmically for n equals 2. For n equals 1, it's quadratically divergent. But basically, you see it from this formula. This will work, and you can expand it, and you find that it's a finite integral. So there's actually no, because the argument gets shifted for n equals 1. This gamma function here is gamma. The d half is 2 minus epsilon. Or maybe not. Maybe it's not. It's not. It's 1 minus 2 minus epsilon, so it's minus 1 plus epsilon. So it also has a divergence.
But we'll have finite parts.
And we also have finite parts. But if you expand this, you will again have a 1 over epsilon. And you will again find this type of log. So naively, it again looks, well, there is a divergence, but it's something logarithmically. All the terms you get are logarithmic. So it takes something which is quadratically divergent, removes this quadratic divergence, and just leaves a logarithmic dependence on this view. Which is again, the quadratic divergence in cutoff would be a big lambda squared. And then this big lambda squared would have to be removed. Here it is already killed, there is no lambda squared. So the only thing you get is the 1 over epsilon. So it works. And this gamma function, it has poles for all negative integers. So and 0. So it's 0, -1, -2, etc. These are the poles. Good. So now we're ready to compute 3 loop diagrams. I mean, this basic strategy would work also there. What I'm saying, you also need these Feynman parameters to combine, and you still need to do these integrals later. So it's still not a simple task because there's more integrals to be done, but one can always do the loop integration itself. Very good. So now we're regularized. So now we can go back to physics. In principle, we haven't done the hour, but this would be a natural place for a break. And then we go to the physics in 10 minutes. So how about we continue 25? So now back to physics. As I said, I want to discuss this renormalization and resumation in the context of Fermi theory or weak effective theory, if you want. And I will consider a very specific process, weak decay of B meson. So B goes to B bar, 0 goes to B plus phi minus. You'll see in a minute why I chose exactly this combination. So just to challenge myself, I left out sort of the quark level quantum numbers that these mesons have, so we can try to reconstruct. For example, this is a B bar, neutral B bar meson. What is the quark content?
The antibody. The antibody.
This is a trick question. It's just to show my immense knowledge that I know that it's the B bar meson that actually has the B quark inside. It's very intuitive.
Is this because the B quark has a duty of -1?
Yeah, presumably it's the other way around. I don't know what yeah, but somehow with D mesons it's the opposite. There's the right way around. So there's a B quark sitting here, and then it goes into a charm here, and then there's this W boson going here. So here, this increases the charge, so to compensate, there's a W minus and then a pi minus. This, I guess, as a D and then anti-up sitting inside in terms of quantum numbers. And since this is a neutral one, this will have a D anti-D quark together. So those are sort of the quark level assignments, but of course this is a cartoon. There's QC, there's gluons and quark anti-quark, there's everywhere. So it's a very complicated process. These lines here just sort of indicate some of these quark flavor quantum numbers which are there. In terms of physical scales, there are a lot of different physical scales now in this problem. On one side, draw the energy axis horizontally. This is the W boson. This is the highest scale in the problem. This is the highest scale where we see some explicit physics here. Then there's, of course, the B quark mass. There were 8 GeV. This is 5. Then there's a charm at maybe 1.6 or so. Then they're all right. Or then there's this this QCD, if you want, confinement scale with all the strong interaction physics. People call this lambda QCD or so. So there's lots of different scales in the game. If you simply try to compute this directly, you will fail. So there's definitely some non-perturbative physics going on just to make these bound states. This you could simulate on the lattice, but the lattice has to work with an upper cutoff of around 2 GeV or so. So down here, you could use lattice, but you will never manage to have a fine enough, but never, not in the foreseeable future, to have a fine enough lattice to include the W boson on it.
When you said that, is that just the technical limit? For
This is the technical limit. So we've discussed this. So they compute this path integral numerically. They discretize, and then the lattice spacing is the highest possible scale. In principle, you can of course make a very fine spacing, but then if you want to cover a given volume and you need a volume which is large enough that this pion fits inside, then you need very many of these points. It's 4-dimensional, so it's 4 to the many points. You have all these color degrees of freedom. It's just too much. So the best they can do is this few GeV range. So they manage to simulate the charm quarks dynamically, but for the B quark, there's already some effective theory, so they have to use eddy quark effective theory or some effective theory that governs this. This process is also special because what happens is B goes into B and this ion shoots out quite energetically. So there's also this soft collinear effective theory that people use, which sort of factorizes off this pion.
Would you not run into this issue if you were just doing B and C by itself, rather than considering the whole?
No, even for B and C with itself. So if you want to do a B by itself, if you want to resolve this energy scale 5 GeV, but at the same time have a meson which has a typical size of this 1 over lambda QCD, you're again hitting this limit. It's just you can do, what the people do is they can work in very small boxes at very high energies on the lattice, or they can work at larger boxes with a cutoff of about 2 GeV. So you can't have, it's just the energy range. You need a large enough volume and a fine enough spacing, and you know how many points your computer is able to handle. So putting this directly is not possible, but you do it in the same way that you do the hydrogen atom. This B quark is heavy and it sits there, and then the rest goes around. So you can use an effective theory for that. And then here, some of these quarks and gluons flying around, the ones that are associated sort of for this W, have a very high energy, and these you can compute perturbatively, and this is what we do today. So here we use this weak effective theory. We integrate out this W, and then we will evolve from this high scale to the low scale. And one problem with having 2 scales is that we'll have sort of alpha S times logs of scale ratios. So you have alpha S times log of MW over MB, or any other small scale. And this is not super large, this log, but large enough that it deteriorates the perturbative expansion. And so these we want to solve today and tomorrow, presumably. That's the program. And I think Matt had some logs where he put a mu. The problem is there are some scales down here and some scales up here. You cannot choose a mu that avoids the logs. So you have logs of MW over mu up here and logs over MB over mu, and there is no mu that avoids it at the end. You also always have these. But using this effective theory, we can first do one scale, then use this evolution, exponentiate the logs, and then continue compute. Good. Now, the reason for strategically choosing this particular weak decay process is that it has so many different flavors here. So the quantum numbers of the operator that mediates this, so it has to be B goes to charm and then up RB. So we have to have operators which mediate this process, and then this severely limits the possible operators, and this makes our lives easier. So, for example, I would like that the B goes into charm fork, like kind of an operator B, and then some gamma matrix, and then a C. So these are the fermion fields, one for the B, one for the charm. And so this operator annihilate the B quark and generate the charm quark. I'm just translating this into an operator. And I also need an operator where I have basically an anti-up going to a down. This here. And I'm trying to make the list of possible operators. That is one possible operator, and then of course for these gammas one can put some combinations of gamma matrices. Here one matrix, gamma mu matrix, gamma mu, gamma 5, etc. So these are possible operators. I could also have these the other way around. I mean, at the end, I have to build some scalar quantity out of fermions, and it has to have these quantum numbers, one P quark in the initial state, one charm in the final state. So I could also write this, change these two. Those would also be possibilities, but then there's a nice relation, the Fields relation, where you can take operators of this form and you can swap the last two, of course. So you can map operators which have this form back into operators of this form using something called Fields relation. So we only need these types of operators. Yeah.
So I'm not sure if you really follow exactly what the use of these others like.
These are really fields now. This is a bit confusing here. In this line, there are just the quarks. I'm saying there is a B quark, it decays into a charm quark. And then I need fields for these, and I'm also calling these fields U. This is just a fermion field. It might have been safer to call this psi U, but then I have to write so many psi's and so many indices. So I'm just writing B, but this is the fermion field for the B quark.
And why exactly is that combination? What those combinations? What you?
In this canonical quantization, you see that the field, the B quark field, annihilates a B quark. So if you have a P meson in the initial state, I can act with this field, and it will annihilate this field. And then this operator generates a charm in the out state.
It's conjugated, is that what it's?
Yes, exactly. That's why it generates one.
This is the game of the A dagger creates.
Exactly. I would have to take this field and write it as Matt did in terms of these A pluses and A minuses. I could usually call D's and B's for the fermions. And some of this fermion operator, it can annihilate a B quark or annihilate the B quark, or it can create an anti-B quark, and the operator does both things. And so I have to write the correct fields to do this job, that I get exactly this quark level process. So, but operators of this form are good enough. Yeah.
So like the way that I'm seeing here, if you look at just the effective vertex, it's B decaying to an anti-up, down, and C.
Yeah, so B goes to charm, is the one thing. And then here, unfortunately, well, unfortunately, here both things are in the final state. So I generate a D quark in the final state and an anti-up quark in the final state.
Okay, okay.
It's confusing that these fields do both, so they annihilate and create different particles.
Yeah.
So, almost do a list. So so psi bar can annihilates B, annihilates a B or generates an anti-B. So you can apply this to the vacuum to generate an anti-B quark, or you can apply it to a state which has a B quark, namely the B bar, and it annihilates it. And then, of course, there are the states and the conjugate states. If you do the same with the conjugate field, then it's meant to be maximally confusing.
And this is one of those insights that you normally don't directly get if you just see a path integral version of your field theory.
Yeah.
Their canonical quantization helps you think about this.
And basically, I mean, all I'm trying to do is I'm trying to basically rewrite this vertex here in terms of an operator. So I'm going now from the Feynman rule in some sense back to the operator. And of course, in the standard model, you have exactly these types of terms with the WO field in between.
Yeah.
But in the effective here, we don't have a WO field, so we have to rewrite this. This is a bit similar to this current operator we had in the Heisenberg.
I just want to check. So that top operator, does it sort of represent that process in quantum diamond?
Yes, it should be exactly this thing here. So I want to later take this operator O, and then I have to take a matrix element where I have B square 0 in the initial state. And then in the final state, I'll have a D plus and a I minus. So this is the matrix element I want to compute. And in order to get a contribution, that these things wouldn't match into each other. If I take the operator away, these are orthogonal states, you get 0. So to map them, I have to annihilate the B here and replace it by a charm. Then it matches the charm here and vice versa.
So on that note, maybe I'm misunderstanding, but the anti-down turns into up or anti-down from this left.
So this one here, I want to, if I start annihilating everything, so this annihilates the B quark here, this thing with the bar annihilates the charm quark here. And so this U here, this D bar annihilates the D in the final state ion, and the up annihilates the anti-up. I think one gets the idea, even though it's confusing because how is the final state? Good. And so we'll write down all these operators, and at the end of the day, we'll compute these matrix elements. And for these matrix elements, you can then use low energy effective series, lattice, and whatnot. Good. So these we said, these we don't really need because we can eliminate them with fluencing.
So this is now an identity. He had the word fields this morning.
Yeah.
Or yes, this morning. That this morning is referred to symbol identity for color. Now this is for gammas.
Yeah, we also need this fields in 1 minute, but yes. So if you have sort of product representations, gamma times gamma, then one can get these relations between the ones and the ones where indices are crossed. Not very interesting, but not so important for us. I just want to try to find the correct operators. And then one can use the fact that this W here is only coupling to left-handed fields. So if you have a fermion field, then the left-handed field is 1/2 1 minus gamma 5. Again, not absolutely crucial. In some sense, we've practiced yesterday how to write operators. Making use of this. So I can put a left here everywhere. And then you know that what remains here, this is this vector minus axial structure. So really the only structure that will arise here is this structure. And this is, we've done it overly convoluted. You can basically have these terms in the standard model Lagrange. And the only difference is that now I have the product. There's still one thing that is a bit under the rug here. There's also color indices. So if you look at this diagram here, then you see how the colors are connected in the standard model. So B goes to charm W, the color, there's no change in color. So this color is connected with this. So this is I. And the sum over this I. So this I is the color index. And then there's another color index J. So this is what I call O1 in my notes. And then there is a second operator. We just said we can fierce around the spins, or we could fierce around the colors, but you can only fierce once. So now we've already used this freedom, so we'll actually get the thing with switched color indices as well. But there's a second operator. And this second one has the color indices the other way around. This I and I. And now some of the experts. Yep.
I was just going to ask, because now that's weird, because then now you can say, since we don't really know what this interaction is, oh, there's color information between them.
Exactly. So how can it be that the color information gets across?
In our effective theory, we have no reason to say it's not allowed.
But you think in the standard model it would not be allowed?
No, not yet.
It will not be allowed at tree level. You're correct. In the Lagrange, there is no such term. But take such a gluon here.
Oh, okay. Okay, fair enough.
So there are high energy gluons running here, and they can change this color. So this operator will be generated, and when we do the matching, we find that at tree level, this as a Wilson coefficient, this has Wilson coefficient 0. So at tree level, this is absent, but actually loop effects generated. And now you could say, well, it's only an order alpha effect. But if you do this running afterwards, this is about 30% as large as the other ones. So these high energy gluons that we integrate out, they have an effect. They make this operator all of a sudden appear and make the coefficient sizable. That's interesting. And the reason that it's sizable is because it's enhanced by alpha times log n W. Yes, so this second operator we have to include, and yeah.
Is there also a second one where you switch one of those ideas? Yeah, was that the same somehow?
Now these are just summation indices. So
I can switch.
I mean, if you take this one and you switch the J's and the A's, it's the same because it's just a renaming of it.
The question is, why if you construct have the U and the B have the same color?
Yes, yeah.
And oh, the U and the B, this is not good. I have to contract the quark and an anti-quark to get a color singlet.
Okay.
So if you have two, I have to take anti-fundamental and the fundamental to make a scalar color singlet. The other,
I guess it would complicate this.
Yes, I mean, these things, they have to be Lorentz scalars. They should be gauge singlets, also gauge invariant. That's why I have to get rid of all the indices at the end, also all the other fermion indices. So I have to form scalars, and the question is how many ways I can do it. And here there are exactly these 2 ways. If you would look at this diagram here, you now know these vertices and they have these color matrices TA. So I could also have something with a TA and a TA in between. That would be a color singlet, but then one can use these color fields. Which I mean, now not writing. These are really the only 2. The entire reason why I chose this specific process is because it's 2 operators, and 2 is a good number. So in 2, I can have the mixing of these operators. I can discuss this evolution. These will mix into each other. It's an interesting phenomenon, but the matrix is still small enough that I can handle it. Maybe the blackboard. Good. So now I have the 2 operators, and now I can write down this effective Lagrange. And there is this effective theory. Of course, at low energies, we integrate out the W and whatever other things there were. And we are forgetting about QED effects, which will be small. So then the low energy effective theory is just the QC Lagrange plus these 2 operators. And let me write the coefficients this way. I mean, there's this Fermi theory GF, which has the V coupling and the 1/mw squared, kind of, well, we're using the 1/mw squared from expanding this propagator. So this will always be there. And then there are other factors. There is a B turning into a charm. So there are CK matrix elements V, C, B. And then UD star. Just in the standard model, these vertices have CKN matrix elements that come with them, the flavor changing. So these will be there. We'll never look into higher order weak corrections. So these will always be just what they are at the tree level. And then the rest. So and both of these operators will of course involve this. That there are ones here. So then there's some coefficient C1, which we'll have to determine, and another coefficient C2. So this is our effective theory. Since I don't want to write this coefficient every time, all this here, G with a hat. All these combinations, these will stay the same and every operator will have. So now the next step is to do the matching, where I determine the coefficients, and in some sense at the tree level, we already discussed what this matching is. Even though I'm not really computing the diagram, this was strategically chosen in such a way that the C1 is 1. I've factored out exactly the thing so that this is just 1 and the other one is 0. So matching at the tree level. C1 is 1. And C2. All of these are always plus order alpha x. These corrections.
Sorry.
Yeah.
On the factor of you said that these were
so these are the CKM matrix element. So the W interactions in the standard model, they come with these factors here. So if
think
you
of it
have,
as a piece of a coupling constant.
yeah, these are there are it's a CKM matrix. So this is the Yukawa couplings that come together. is directly read off this final rule. So if you open your big standard model book on page 250, where these rules are, you will see that this vertex has a BCD. And then in the other case, if you bend this, this is up going into down, and then it's the complex conjugate of
These are CKM allowed. These are close to one.
these are yeah, I could. This is quite close to one. This is also not so far. So this is a nice decay, it's not something rare. This is quite a typical decay for and I'm sort of interested in this QCD corrections. That's why I'm sweeping this a little bit under the rug. But this part is the same as in the standard model, and it's really just read off from these final rules. And we could compute these diagrams. You would have exactly this, and then you would have this propagator. And then in this propagator, there is a 1 over p squared minus mw squared. And since these have all very low energies, we expand. So we get a 1 over mw squared. And maybe I can write the GF. This is just G. How do you want me to call it? The SU2 coupling squared over 8 mw squared. So if you have the standard model Feynman rules, you have the SU2 coupling, and from expanding the propagator, this and these are go along, and then you need it to get this. Good, so that was the tree level. But now we're ambitious and we want to do the one loop matching from the full standard model onto our two operators. And we've indicated this yesterday. What we have to do is we have to compute 2 times the same quantity, once in the standard model and once in the effective theory. And then we simply adjust these coefficients C1 and C2 so that we reproduce the full theory result. And so it's kind of natural what to compute. We just compute exactly this closures here, but of course not with B mesons. That would be possible. We simply compute with quarks now. So we just compute same at the quark level, B to jar. And the other one was up. I've now taken some of these lines instead of an unpacked up in the final state. I'm taking it up in the initial state. The diagram is drawn easier. So this is the full theory. The basic process, and I have to compute QCD corrections to it. So there are different diagrams. I can exchange a gluon here. Exchange the gluon between the other lines. Start here and end up here. And then, of course, instead of having this at the upper vertex, I could have it at the lower vertex. Instead of having it on the left, I could have it on the right. And so this is plus mirror diagrams. So it's 6 diagrams that I would compute. There's also diagrams, of course, where you have corrections on these external legs. These you could compute, but these will be the same in the effective theory, so in the difference they will actually drop out. But, so that is the full theory computation. Now the effective theory computation. looks very similar, except that we don't have this W in the middle. So we have our operators like this. So here is the operator O1 or O2. And then we can exchange a glue on here or the other possibilities as well. These diagrams. And I have to compute those twice, once with the operator O1 and once with the operator O2. And again, plus the mirrors. Now there are different ways of doing this computation. I have to say I compute the same thing, and I've decided to compute this 2-to-2 scattering. That is a possibility. And I can choose the kinematics to be as simple as I want. So a very nice kinematics, even though it's not exactly scattering, would be to set all external momenta to 0. That would be possible. If you set all external momenta to 0, and you can also forget about the small quark masses, you can compute with the quark masses, but this part will then be the same in the full and EDF effective series, or we can just say, let's compute with massless quarks, it will be good enough. So set all quark masses to 0, set all external momenta to 0, then actually all these diagrams would be scaleless. So then the effective theory computation would be fantastic. So the effective theory computation would be equal to the 3-level result. I mean, it's always, we compute this plus 3-level. The 3-level can also contribute because there are other alpha terms sitting in these C's. So that would be very easy, but somehow not very pedagogical to have this range to make use of this fact. So I will not set all momenta to 0, but I will set all external momenta. So there are 4 external momenta. I will set them all equal to some pi, to some p, and I'll keep this a little bit off shell. So I'll take external momenta p, another one, and this p squared is not equal to 0, maybe slightly negative.
So the reason you're considering radiating corrections is because you're not actually able to calculate the cross section, and you just want to match.
Exactly. I can do this matching on the level of amplitudes. That's easier. The question is basically, what is the simplest computation you can do in both theories to get this? The most complicated computation you could do is to compute actually 2 full meson decays with everything non-perturbative. So you take 2 different decays, would extract the 2 structures, and then adjust the coefficient. So that would be a disaster. But instead, I'm saying, the simplest thing is I'm computing this amplitude or amputated Green's function. I go slightly off shell. It's not even really a great physical object. Or it's not really a physical object. Still, I can just compute this in both theories. And it's good enough that I can match the coefficients. And this slight unphysicalness here, in this example, will just drop out in the difference, because in some sense, I'm interested in the difference between these 2 things. If I would be smart, I could even say, well, this diagram will never contribute to this difference because it's the same. So I could even not compute this. So there are tricks to simplify this. But we will not do it because it's still painful. But I want to show you the result. And since you now know this dimensional regularization, you can appreciate some of the features of the result. Sad. Proud of this beautiful drawing. It's time to delete it. You remember the 2 operators? So I call this amplitude, or if you want, better term would be amplitude, the Green's function, I'll call this gamma. Of course, the result has this G hat up front with all the CKMs. Anticipated, and now there's the tree-level result, and there are corrections. The tree-level result I can write sort of as the expectation value of this operator O1. I can take external quark states that is exactly this thing. So this is just so that I know what is what. At the lowest order, this was a 1. We said only this operator will arise. This is how we read off that the C1 had to be 1. And then at one loop level, I get this 2 times CF 1 over epsilon log V squared over P squared. And then second, this is actually the first diagram here. And then the other diagrams. There's an alpha S over 4 pi. The alpha S is the G strong squared over 4 pi. And now there's an interesting term. So we see that there's a log of MW squared, as promised. Then 3 over NC 1 3 minus 3 times 2. And to make things short, I only write divergences and logs for the moment. There are also some constants floating around. Let's say what it's later, but so these are the important things. We found divergences. The divergences are only from the first diagram, actually. The other 2 diagrams are finite. Why? It's a quiz question for the audience. Why can this diagram have a divergence? We counted these denominators and then we said up to 2 propagators is divergent because it's 4 d4k over k to the 4th. But this is a triangle diagram, so it has 3 denominators. Why can this be? How can this be divergent? Yes, we'll in a moment we'll renormalize this away. But why is the diagram itself? Why can it? It's a triangle, not a self-energy. Why is it divergent? In the first hour, we said only this n equals 2 can be divergent. The n equals 3 with 3 propagators. This is fine.
Check out what particles are and what the properties ought to be.
This is a bit an advanced question, so it's for people who have had QFT. They should be able to. The other can relax, relax for a second.
Think for a second about the differential equation for a gauge boson versus the differential equations for a fermion. What's the dimension of the differential operator? Complicated is the inverse. Complicated has the inverse dimension.
Yeah, exactly. So that Heribert is a very good student. So the fermion propagator, so it's the propagator is always the inverse of the quadratic piece in the Lagrangian. So it's psi bar ID slash psi. So it's actually 1 over p slash, and of course plus minus m. This is the fermion propagator, and of course you can write it in the usual form. One can write it as p slash plus m over p squared minus m squared by multiplying with p slash plus m both sides. So there is this denominator, but there's also a numerator. So it actually only goes like 1 over p. So this is 1 over k squared, 1 over k, 1 over k. So it's divergent. That's why there is a diversion. While for these box diagrams, there's one propagator more, and this is okay now. These are finite. That's why these diagrams, the other two, just give a nice finite result. Okay, now let me write. There's some things which I should explain. I've smuggled in this CF without any explanation. This is a color factor, so this is just NC squared minus 1 over 2NC. And this is because when you exchange a gluon, you get a product of two such color matrices TA, and this can be written as F times 1. This is called the fundamental Casimir for the group theory friends. But yeah, so some are not unexpected. We have two strong couplings in the diagram. This is what this alpha S gives. There's some algebra with these colors, which gives the CF. Also more complicated color factors like this 1 over NC. NC is the number of colors is 3. So now effective theory result. Again, this G hat is everywhere. Now I have C1, and then I have C1 times 1 would be the tree level times this tree level matrix element. So we're now not using that this is equal to 1. We want to read off what it is. So, and then there are loop corrections in here. So there's from the first diagram in the effective theory. This is this first diagram, and I basically said it should be the same as the full theory. Let me see whether that is true in my notes. Yes, 2CF 1 over epsilon plus log U squared over P squared. So indeed, this is exactly the same thing. Alpha S over 4 pi. And now what is more interesting is the other two diagrams. The other two, they're not exactly the same. So they have one propagator less here. So here you have the W propagator. So no UV divergence here. This propagator is missing. So this is like a triangle. And so not surprisingly, now we get the divergence again. And this is the divergence which was not there in the full theory result. 1 over epsilon plus log U squared over P squared. Minuses here. And 3 over NC times the matrix elements operate, and it's 3 times matrix element of the same. And then the same thing, but with 1 and 2 exchanged. And so as advertised, there is this extra divergence here, which was not there standard model computation. Now you already said that this divergence, as presumably once you do this wave function renormalization, this should go away, and this is true. So now we can do wave function renormalization, which will cure this divergence. Question is how to go back up and down with the backwards. So I said that in this renormalization process, the divergences are absorbed into parameters of the theory. But in addition to the parameters like the mass and the coupling, we can also absorb some divergences into the normalization of the field. And for a quark field, what one does is one takes this quark field, the one that is in the Lagrangian, and says, well, this field, this is the Becher field. This is Becher before renormalization. This contains divergences in its normalization. And I'll introduce the factor ZC like this. That is supposed to absorb these. And this psi here is then the renormalized field. It should have a finite norm. In some sense, this is a bit arbitrary. This field is anyhow not directly a physical quantity, so you could also not do this renormalization, but people like to do it so that the field is properly normalized. And so this Z psi, this one can compute by computing the self-energy of a quark. So it's 1 minus alpha S over 4 pi CF. So this one can take from a textbook. We have 4 of these fields. So when we do this procedure, we'll get a factor of this squared that is now multiplying our Becher result. And you somehow see that this works out. So here it's plus CF1 over epsilon. And since we get this squared, if you expand in alpha S, you get minus 2 times this. So these divergences here get cured by wave function analysis. So this gets cured. So this is wave function normalization. And the same thing in the effective field theory. The leading order Lagrangian is QCD. So again, this is cured here. But this leaves us with this divergence here. So this stays. And maybe I've already said it, where this will go. This we now have to absorb into the parameters of our theory. And the parameters we have here are the couplings, these Wilson coefficients C1 and C2. So we have to renormalize these coefficients C1 and C2. And we have to say, well, these basically like the field here, these are really Becher coefficients. I can also put a 0 here. Somewhere there should be another C, otherwise it doesn't make sense. Now, everything is C1 here.
The C2 thing you didn't write.
The C2 I didn't write because it's in this 1 goes to 2. So this is the Becher one, and now I will define a renormalized one. This will be 1 plus something divergent. And then if I plug in, expand, I choose this exactly such that it cancels this term. Yes.
I don't think I fully understand why the divergency disappears. So in the effective theory, it disappears there, but it stays in the other term.
It's just this wave function normalization. This will give an overall factor. So instead of sort of this Becher gamma, we'll now have a renormalized one obtained by multiplying with this Z squared. So doing this, basically, I have to now multiply by the Z squared, and then I could call this one properly normalized.
Wouldn't that distribute to that term? The divergency term.
Oh, it's an overall term, so I multiply everything by this, and then of course I expand in alpha s, and so the only thing I have here at the lowest order is a 1, and so everything that has 2 as alpha s squared gets thrown away, so it's this factor times this 1.
Okay.
And if I multiply out, then I get here the minus, and it cancels the plus here, and you get.
And everybody else has an alpha, right?
Yeah.
It already has an alpha, so it
Yeah.
never sees this. It would multiply, but then you get alpha squared, so it doesn't help. So these really remain. And so we have to do a second renormalization step, where I say, well, my effective Lagrangian, we've written it as this G, and then we add C1 times O1, C2 times O2, but it's now better to use indices, so this is like a vector, and I'm summing over this I, 1, 2. These are now these pair coefficients, so they have to absorb divergences, or you would say these are divergent. And now we want to rewrite this in terms of renormalized coefficients times a set. And now is the important point, this set here is just a number, but here we have these 2 operators. So just saying it's a number is not good enough. So this has to be a matrix set Ij. This contains divergences and then multiplies this. J. Exactly. And in this case, again, this will be expanded in alpha s. At the tree level, this is just a unit matrix. So this set Ij is equal to unit matrix delta Ij. Plus alpha s over 4 pi, and then some matrix set Ij. So the one loop terms, then plus. And now, if we had 2 blackboards, we had a bigger blackboard, we could try to read off.
You could take, if you want to, you can take one of these things away.
Yeah. But it's too late. We'll just go up and down a little bit. So I'll write this Cij. This is a 2 by 2 matrix with 4 entries. On the top left, this is the divergence of the 1 operator proportional to the 1. So here you have that this was the contribution from the operator O1, that's why it has the C1. And some of the divergences are proportional to O1, and the coefficient is 3 over NC times 1 over epsilon. So we need exactly the opposite, minus 3 over NC times alpha over thing times the 1 over epsilon in order to do this. So 1 over epsilon minus 3 over NC. And then the other one is divergences of C1 proportional to the operator O2. This is a minus 3. To cancel it, we need a plus 3. Now we would have to do the one with from the C2, which looks identical up to the switch 1, 2. So matrix looks like this. And so plugging this in, let's see, and still. But the Zoom audience is no longer that big. So now plugging this in, I can read off these renormalized coefficients here. Ci renormalized. So this will be the tree-level coefficients plus alpha s pi times the coefficient. Don't put too many indices on it. And this can be read off now. So I've done the renormalization, and I want that the difference gamma full minus gamma effective, this has to be 0. So this is the matching. We have to adjust the coefficients C1 and C2 so that this difference vanishes. And let me write the result for C1. Is 1, C2 is 0, and then there's the alpha over 4 pi corrections. Now we should be able to read off. So the divergence has been killed. In the full theory, we have an mw squared over minus p squared, this log. In the effective theory, we have a log mu squared over p squared. When we take the difference, this p squared here drops out, and the log mu squared over mw squared remains. So 3 over nc, and then log mw squared over u squared. And for the other one, there's the minus 3 log, the same log mw squared over u squared. I did not write the constants here. There are also constants, but the constants are interestingly 11 over 6. It has nothing to do with the functions. So it also these constants are somewhat scheme dependent. These coefficients are not really physical quantities. The fact that this p squared dropped out was very important. So this p squared is low energy physics, and we've chosen the most trivial way of doing low energy physics with this small offshowness. This has dropped out, and we've now got this coefficient. This coefficient only depends on mw. This is good because this coefficient encodes the high energy physics from high energy gluons. These high energy gluons only know about mw. And so our operator has a 1 over mw squared here. That's the irrelevant operator. But then there's also this small logarithmic dependence on mw. And so the dimension of this operator is 6, but then there's some hidden other dimension. This is called the anomalous dimension of the operator, which has to do with the fact that there's this other mw dependence. And you see that after this cancellation and renormalization, this coefficient now depends on mu, this scale that was introduced. The physics at the end of the day cannot depend on mu. This mu was sort of an auxiliary scale to have the usual dimensions we saw when we did thing break. So this has to drop out, and this gives a condition. So there's an equation that tells you how this evolves with mu, and it evolves with something related to this anomalous dimension matrix. And so this we will look at tomorrow. So we now have determined this coefficient at this high scale. We can write an equation or derive an equation from this renormalization condition here. this pair stuff did not depend on mu, so the mu dependence has to cancel out here. This gives an equation. We solve this equation and we resum all these logs of mw squared over u squared. Good. So this is maybe the most technical part of my lectures. You survived. Life should get slightly easier tomorrow. This Archie evolution is still a bit technical. It's in the notes, and then we've done it. But I think it's nice to see this. It's so nice to see this anomalous dimension appearing here, and then to solve this equation.
Good. Thank you. Do you have any urgent questions?
Technical question. You set p squared to 0 from the beginning.
Yeah.
So, but would you get the log mw squared or u squared?
If you set p squared to 0, then the entire effective field theory part would be gone. So the result would be 1 and nothing. And of course, this p squared to 0, this leads to infrared divergences. So you would have infrared and ultraviolet. So in some sense, the 0 would be a 1 over epsilon UV, which is this thing here, which we renormalized minus the 1 over epsilon infrared. And you get a 0. In the full theory, there would be a p squared. So this would also be 0 conveniently. But you would get an mw squared, this would still be here, and then over mu squared. And so you would basically directly get this result. In the full theory computation, there would now be this infrared divergences floating around, so you would feel a bit uncomfortable that this happens. But actually, these infrared divergences would cancel against the infrared divergences here. So if you're confident, then you can do it this way and you would get the result more directly. But then the computation will evolve also some infrared divergences. But they're regularized by DIMREG, so it's fine. And all the professionals, of course, if you do this to 3 loops, which people have done, then you will have to make your life as easy as possible. So you will set everything to 0 that you will set to 0. So you will never compute any effective theory here. However, if you want to know this anomalous dimension, you will actually still compute this type of diagrams, because you want to know what the divergences of these operators are. So there would be still some computations that you would separately do just to get the anomalous dimension.
Can you speak a little bit about this cancellation of the epsilon UV and epsilon IR? That's always been a little bit uncomfortable for me. So
yeah, it's a bit
some kind of an artifact of that choice of the integral over dimensional integrals all being 0, or should I really think about this as the UV physics and the IR physics are actually completely divergent?
Yeah, you can have an integral from 0 to infinity. Let's say dk over k. You put some epsilons or not. And then, of course, if you put this epsilon here, now it's in this category of regularized integral that gets regularized to 0. So this is 0. But you can, of course, write this as an integral from 0 to 1 and an integral from 1 to infinity. K over k1 plus epsilon. And you can separately compute these here now. The first one is clearly an infrared divergence at 0, and the second one is a UV divergence, and you would really get from this integral a -1 over epsilon, and from this integral a +1 over epsilon, and you would recover the 0 to do it.
This is where I get really comfortable with, because the sign of the epsilon is different. Maybe that's exactly where the minus is coming from.
Yeah, well, it's from the different boundaries here. I mean, first of all, to do the integral, you of course have to choose different values of epsilons for the first and the second. The idea is choose any value where the integral is defined, and then analytically continue to the full complex plane.
Yeah,
so this is what
there's exactly no place where those You have both of those integrals.
Yeah,
converging
no
at the same
point
time.
where there's overlap. For one, you have to go into this region, but then continue to the full. For the other one and another, continue to the full plane, and you get 0. This shows that it's all consistent. So this works. Whether you feel comfortable, it's a different story. So it's psychologically hard, but well, no, that it works consistently. So you can indeed take one of these scaleless integrals, split it up so that you have integrals with scales that are well defined, and at the end everything would add up. It's also when you use the usual rules of computing in dimensional regularization, it will often happen that some UV divergence can turn into an infrared divergence because you added and subtracted things. It's actually quite difficult at intermediate stages to track this. And of course, calling this one an epsilon infrared and this an epsilon UV, this is a bit artificial. You have only one epsilon. So this is a bit hand wavy. It's not clear that you can consistently do this at 7 loops, but at the 1 loop level, it's simple enough.
All right. Let's break for an hour.